Hello, everyone, and welcome to this ATA webinar for this afternoon. Thank you for joining us. We're going to be talking about STAR-CCM Plus and Meshless DEM. We'll be going through a little bit about ATA, a little bit about STAR-CCM Plus DEM, and then I will pass the ball to Max Hewkin-Greggor, who will be walking through an example of setting up a problem like this in STAR-CCM Plus. So, Max, thanks for joining us.
Good to be here.
And with that, I will briefly go into a very short presentation about ATA. ATA are an employee-owned engineering consulting group. We're a small business with around 180 staff that's growing continuously. And we have a very highly skilled set of employees with a large percentage of PhDs and so forth, and really excel at doing the hard problems for our clients in the engineering space. And the engineering areas we work in are aerospace and defense is our primary area, but robotics and controls, themed entertainment, and mining and consumer products are other areas where we work. So it's an interesting, diverse group of areas we work in. And we are an employee-owned company, which we all enjoy the benefits of that, but what that means we also take every project we tackle personally and really work through communications and many other challenges going with those kind of things, and to strive for customer delight. And many of our clients echo that they see that continuously on a day-to-day basis. And occasionally we are recognized in the industry. The most recent award there is the SBA Tibbets Award that we got last year, basically for an excellent rating generally. So you can see that we tackle things at a high level and we get recognition for that. And so what do we generally do? On the services side, our focus is on analysis and test-driven design. And we're really proud to help our customers meet their toughest challenges, from performing ground vibration tests on state-of-the-art aircraft, through to theme parks and safety on theme park rides, to analyzing next-generation spacecraft and Mars rovers. And really, part of that is that we're also experts at Siemens software, and hence our webinar today. And we really use all of those tools in the work that we do. This slide really just to highlight the legacy of depth of experience at ATA. Originally, ATA was a division of STAR-CCM, and for those of you who might remember that was the group that created unit graphics and ideas. And in 2000, ATA became a separate entity coming out of STAR-CCM. The other thing to note on here is that in 2009, ATA became a full partner with Siemens, a VAR, evaluated reseller, selling NX. And then in 2018, we added STAR-CCM Plus and HEEDS, and mostly because we have people on staff working on all of those products at a very high level on a day-to-day basis. So on the software side, basically we do full support, full implementation. We also are very highly skilled at NASTRAN and FEMAP. We do a lot of NASTRAN training material, about all of the NASTRAN training material for Siemens. And we're also a training provider for all of the SimCenter products that we support. So today we're focusing on STAR-CCM Plus, but we do many other products within the Siemens portfolio of tools. So today I'm going to talk about STAR-CCM Plus DEM, discrete element method for modeling particles. And really, I'm going to start at the very beginning and ask why is it necessary today? And really, these are some boxes that kind of discuss the industry overall. Increase in product and process complexity, operational efficiency, cost reduction, and innovation. I'm sure all of these questions are something that come up in pretty much everyone on this call. And so, what does that mean in more detail? Well, really, machinery is getting more complex, and the physics is also getting tricky. So there's more challenges in design than ever before. Handling time reducing, and really the quality control is obviously getting tighter all the time, and so reducing particle breakage and spillage. DEM can model impacts and damage to particles. And also lower cost design when you're designing a machine to move particles around, bulk handling, lowering the cost and the operational cost as well as maintenance is all part of the challenge. And then really, one of the things we see is a lot of new materials are coming out that we're asked to model. and sometimes getting that data is a challenge, but really it's the innovation of being able to model new materials that is very exciting with STAR-CCM plus DEM. And so when we take those challenges, which pieces of the STAR-CCM plus model help us do that? And really, STAR with DEM can predict and model real world behavior of particles and particle transport. And if you can do that, and you can do it with a realistic accuracy and have faith in that model, the next step is then to basically run it many times and look at design variations. And it's very much part of the Siemens kind of mantra, and especially with STAR-CCM plus, that all models are mostly automated to the point of view when you want to run the next version with maybe a different particle velocity or a particle size, all of the pieces in place to run it very quickly again. And so if you want to run 100 different variations of a chute design with different scales or different sizes, it's very straightforward to do. So automation is a big part of STAR-CCM plus, and really, with those two pieces, having a model that accurately models the physical situation together with the easy repeatability of that, you have a tool that can really give you good results. So how can we use DEM in the real world kind of thing? And everyone on the call has their own answer to that, I'm sure, but there's obviously a lot that can be done, and I won't read the list because you can see it, but it's very diverse in terms of the types of applications that you can apply DEM to. And really, we're going to look at some more of that in detail with Max's presentation as well. And so this is like a very standard version of why DEM is useful. And this example is basically a pill coating machine, and it's basically a tumbler, a dryer and tumbler with a spray inside to coat tablets. And on the left is the first design, and obviously there was some damage and some problems with the actual pills being damaged in the rotation. And on the right is the final design. And in the middle, even though it looks like it's a video that's not working quite correctly, it actually is a video of different variations of geometry that were tried in the process of improving the design. So the one on the left is the baseline design. The one on the right is the final design. And STAR with DEM automatically evaluated 35 different designs, mostly with geometry changes on these baffles, and basically created a new model with 21% increase in coding rate and a 44% decrease in tablet damage. So, and that would have been run totally automatically without a man in the loop, on a computer system, could have been in the cloud, but really just left to run and evaluate new designs. And so this is where we see the real value of simulation generally, but especially STAR and STAR with DEM. And so if you want to do all of those things, what are the key requirements that you need to be able to tackle? And clearly, if you want to do particles, you've got to try and model all of the particles that are out there that might come in down the road. So STAR can really deal with lots of different particle shapes and sizes, using basic primitives to build them and come up with more complex shapes. And you also need to consider the surrounding area of action. Obviously, with an excavator, like you can see there when you saw the animation at the beginning, you've got to be able to model the motion of the excavator together with the bucket impact on the particles. And also on the right, maybe a shaking boundary or shaking conveyors that move particles around. So boundary types and motions are critical. And then today, this one's relevant because we're going to be talking about meshless CFD. But if you want to do coupling fluid flows with the particles, blowing sand around a sandblaster or silt in water, then you need to model both the DEM particles together with the fluid flow. And STAR, that's how it started, really, probably 10 years ago, where they could exactly do that with STAR-CCM plus, and really has come a long way to where we are today. Multi-phase interactions, you can see really the picture on the right there of the ship in an ice flow tells the story of why this is useful. The ice on that image is particles, DEM particles floating on the free surface of water. And really the great thing about the DEM modeling is that it works with nearly all of the chemical models and all the physical models in STAR-CCM+. So if you want to do particles with electromagnetism, if you want to do paint particles landing electrostatically on a body, pretty much all of the models that are within STAR also work with the DEM model as well. So it really opens up a lot of opportunities for that. And then obviously, these can get to be big models. You can see the particle count on the left there in terms of tablets or particle count. 200,000, it seems like a lot, but 20 million obviously is a huge amount. If you wanted to run 20 million on one serial processor, 88 days is clearly not acceptable. So the parallel scaling of STAR-CCM+ with DEM gets as much attention as really the general parallel scaling in STAR. And Max, I think, can talk about that a little later. But nonetheless, the parallel scaling on the DEM piece of the simulation is very robust and continues to improve each variation, each release of STAR. And then lastly, how do I look at all this data to firstly be interesting and make it possible for non-engineers and non-analysts to visualize the results and see what's going on. And so STAR, using all of its post-processing tools, including history data files to preserve each time step with a complete data set, together with screenplay to do really advanced videos, really takes the results visualization to the next level. And so if we look at all of those, let's kind of dive a little bit more into each one of those quickly before we pass the ball to Max. And so if we look at particle types, that there are particle primitive shapes that really are the building blocks to any particle in STAR, and they can be spherical, cylindrical, or polyhedral. And in fact, STAR has the ability to read in an STL geometry file of a particle shape, and then basically fill it full of primitives. So you can create a rock shaped, really any shape you want out of the primitives. And then you can use composite particles to actually make bigger particles into one. And that picture in the middle on the right-hand side shows you how that might come together. They can break apart also by particle clumps. So that if you really, and all of this comes to saving compute time rather than modeling every particle at the same time. And then lastly, identical cylinders bonded end to end. There's been some interesting things in the last few years of modeling fibers, and also there's an example last year of modeling a lawnmower cutting grass using DEM bonded particles to represent the grass and the cut, together with the CFD fluid flow of the air within the mower bed. So very interesting stuff. Now, I don't profess to be an expert on contact models, but STAR-CCM+ does have all that you could probably need, and really the most basic one is the Hertz-Mindlin one. And I'll cede that to Max to talk about later if anyone has any questions on the contact modeling. But really, there's a complete set in there that give you what you would need. And then again, you've seen these videos at the beginning, that the coupling between DEM and the particles, in many situations, it's essential. You've got a fluidized bed, you've got a filter in a flow on the right there that's actually blocking the flow. And so being able to model both is a unique part of STAR-CCM+ in one tool, in one simulation. It's very quick, it's very easy to access. If you've got big particles relative to the CFD mesh, then you can do source smoothing across those particles to actually make the results more accurate. But nonetheless, the DEM CFD coupling has really been the strength of STAR for 10 years now. And just recently, we're seeing the meshless DEM that we're going to focus on in a minute. And then obviously, if you're going to do moving boundaries, that opens up really everything to help you do real world examples. So, if you want to do grates and filters that are shaking, things like that, if you look at the videos in the middle of the top left, then conveyors on the top right, you've got to be able to model the conveyor belt together with the dynamics of that motion. The excavator, both excavators, how do you model that motion? And so moving boundaries are a big part of STAR-CCM+. Really, you can see the list of things. You can sliding mesh. The most interesting one, I think, here is the mesh morphing one on the bottom right, and that is often used in the oil and gas industry of a sand and kind of oil and water slurry mix in a pipe. as the sand erodes the pipe away, the actual geometry of the pipe changes. And so using STAR, you can model the erosion process with DEM. And as it changes the pipe geometry, you can then remesh the fluid domain to actually equate for the removal of materials. So it's pretty advanced stuff. And then lastly, the chemical side of things and the multi-physics side of STAR-CCM Plus is also completely compatible with DEM. And so in this case, on the right, these particles are falling into a bed. This could be sand and falling into liquid glass. I'm not sure if those temperatures would represent that, but either way, it shows melting particles into a fluid. And obviously the mass and all the other physical properties are maintained across that. So when a particle of a certain mass melts into the fluid gains that amount of mass. And so there's some surface tension models in there. There's lots of advanced things to help you really tackle this kind of multi-physics modeling with DEM. And then lastly, we talked a little bit about parallel processing. It's fully parallel, and there are some optimization settings to help it make it go much faster. And you can see on the right there that there's a 5 million cell problem of a hopper filling with air and discharging. Took 21 hours on almost 100 CPUs. So that kind of problem needs a decent HPC system to run, but 21 hours isn't too bad. And so really the last thing we're going to talk about, and passing the ball mostly to Max at this point, is mesh-free DEM. If you're actually modeling both pieces of this, obviously there's a mathematical overhead and a compute time overhead. And so moving to DEM without the CFD mesh takes a lot of the calculation out of it. And this is what Siemens are reporting an average of 5.5 speed up time for simulations with complex motions, which is obviously significant. Certainly if you're running a matrix of different designs where a lot of them can add up to weeks and days instead of hours. And so in summary then, basically STAR-CCM Plus with DEM can tackle and predict the real world behavior. And it can also tackle many design variations easily and quickly to really help in your early development. So with that, I'm going to pass the ball to Max. And thank you for your time.
Thanks, Adam. So I'm going to talk through today this example case of using the new mesh-free DEM capability within STAR. We came up with this case, completely kind of arbitrary case, to demonstrate several capabilities and mostly to show kind of how quick and easy it is to run STAR with DEM if you don't have to worry about a mesh. It saves you a few steps in the process and still leaves you with a very powerful tool. So what we're seeing here is a pill conveyance system. So we've got these purple capsules which are passing along a conveyor belt. Maybe they've come from some manufacturing process and that's produced some debris, which is these yellow spheres that we're seeing. And so we want to get rid of these. So we've designed some filters that are meant to filter them out. Now I didn't do a very good job with my design, clearly, because it's not filtering many of them out at all. And they're all ending up along with the pills in this tip at the end. And we're going to use the DEM boundary force model, which is going to basically measure the weight of particles within that tip. And once it reaches a certain predefined amount, it's going to tip those particles into the bucket. The bucket's again going to measure the weight that's landing in it. And once that weight stops changing, because the bucket's stopped, the tip stopped tipping into it, then the bucket will move along and kind of model a random sort of conveyance and a manufacturing system. And this is all done without having to produce a mesh. So this is the workflow I'm going to talk through. I'll focus more on the stuff that is more generic to any problem rather than some of the more specifics. Like once we get into the motion of this case, there was quite a bit of setting up to do for that. because of the way I'd set it up, but I'll kind of gloss over some of the more specifics. And the other thing I should say is that this is a completely kind of, we came up with this geometry. It's completely open, so we're able to share this sim with anyone who is interested and might want just an example of how the process works and be able to just look through the sim themselves. So we'll start with the geometry and work through kind of setting up the domain and the physics. Spend a bit of time looking at how the multi-phase particles and their interactions are set up, how we inject them, and then finish on some settings and the motion, and then show what the results look like in visualization. And for most of this, I've pre-recorded some videos of me clicking through STAR, so you can see exactly how quick it is. I would say probably would take maybe 40 minutes to do this. So I've skipped over a few steps, so I don't have to watch me clicking around for 40 minutes. But in general, this is pretty much in real time how long it would take to set up this calculation. So with our geometry, we could create it in an external CAD software and import it. That takes about 3 clicks, file, import CAD. In this situation, I've created the geometry myself in 3D CAD within STAR-CCM+, and you can see the geometry as we saw in the video just now here. And you can see on the left the tree of operations it's taken me to produce that, some revolves, extrusions, and patterning this this bucket. And I've ended up with several parts. So we had the feed funnel, the conveyor belt passing over 2 filters into the tip, and then finally all these buckets are a body group here. So that's the geometry we're going to start with. So we could have made this ourselves, we could have imported it, been sent it, whatever. We've got it into STAR. It's taken us a couple of minutes to do that. And the only stage we really need to do before we get into setting up the physics is defining our domain, which is effectively the region in which we're going to solve the physics and solve the particles. So in this case, I've just drawn a sketch around the region of interest, which is just after the particles, or where the particles are injected, the conveyor belt, the tip, and the bucket. And I've just extruded a region, extruded a solid body around the area. And with Meshless DEM, we only need one solid body, and that defines the domain. Everything else can just be surfaces that we define as solid surfaces. So we don't have to worry about having a single solid body without any leaks in it. We just create one that defines our domain, and it could have just been a block. I didn't need to draw that complex shape around the domain. It could have just been a block. But in order to keep the compute time down, because my initial design was spilling particles everywhere, I didn't want to be resolving those falling for ages. So I created that smaller body around. And then what I need to do is just pull those parts out from 3D CAD into kind of STAR-CCM itself in the parts tree, and I end up with these few parts. And the one final thing I need to do before moving on to the physics is I'm creating, using a subtract operation to add some extra surfaces to that block within it, which are the surfaces of those filters, so that later I can define that when the particles hit those filters, they just get removed from the domain, because I'm filtering out those things. I don't care about them anymore. I don't want to be resolving them falling through to the bottom of the domain. So I just created those surfaces within the domain, and that allows me to create to model those filters later on. Okay, so on to the physics. We can skip the mesh. The mesh is, don't need to do a mesh, just straight to the physics. So I call my physics DEM. I go to select models, and I just find the mesh-free DEM at the bottom, and it will pre-populate everything I need. I'm also going to select DEM boundary forces and gravity. The boundary forces model we're going to use so that we can measure the weight within that tip, and therefore use that to define our motion. So we selected our physics. The 2 things that we're going to need to do later are define our Lagrangian phases, so that's our 2 types of particles, and then define how they interact with each other, themselves, and the walls. But before we do that, we need to define the walls. So I've got all my parts. One thing I need to do beyond what I did in creating them within the CAD is I've got my conveyor belt here, and I'm just going to split that up into some different sections. because they're all going to move in different directions and at different velocities. So just split that up, and I will have all the surfaces I need to be able to define the motions of the conveyor belt. So now I can start to create my regions, and the regions are going to be those that move separately, or those that or the domain region, which defines the area where we're solving. So for the conveyor belt and the feed funnel, they're going to be stationary. We're just going to prescribe motion along some of the surfaces of the conveyor, so I can create a region for them. For the buckets, I created one region because they're all going to move the same or move together. And then for the domain and the tip, I'm going to create a separate region for each of those. So we're going to end up with 4 regions in the simulation down in the region tree: the domain itself, and then what I've called the walls domain, which is the kind of stationary parts, the bucket domain, the bucket region, and the tip region. And for the walls, the tip, and the bucket, we're going to set these to, I'm just going to skip back there. We're going to set them to solid regions because they're just surfaces. The particle region, we're going to leave the domain as the particle region, is the region in which we're going to solve the particles, and that's the only one that has to be a solid, like in a typical CFD calculation where you have to have the enclosed solid. The rest of them, these are all shell parts, and it doesn't matter because we're setting them as a solid region. They're just going to be surfaces. So by selecting the mesh-free DEM, it's restricted all our options to everything we need, and it's not overcomplicating things. We're not able to set these regions to be different regions that they wouldn't be compatible with the model we've chosen. So we've defined our parts, we've defined our regions, we've set up the physics. Now we need to say, what are our solids going to be? So creating a new phase here in the Lagrangian phases, I called it spheres. I'm going to select the DEM particles model. There's nothing else available because we're in meshless DEM mode. And I'm going to use spherical particles. There's lots of different options here, but spherical particles are the most basic. I'm not going to model any erosion. I'm not going to track the particles. I'm not going to use any of these other optional models, but they're all available if you needed to track your particles or you wanted to model erosion. So the only thing I really need to set is the material properties, and I'm going to call this solid pill bits of pills that are broken up. I'm going to set an appropriate density, and then I'm going to leave the Young's Poisson's ratio as it was. I'm going to cheat a little bit here and set the Young's modulus a little bit lower than it really is, just because that speeds up the calculation a little bit for this demo, so that I had a quicker turnaround time. And similarly for the wall, I'm going to drop the Young's modulus quite a bit on the surfaces just to get that going a bit quicker for this demo purpose. But in reality, you could just set it a bit more representative, and it would just take a little bit longer to solve. Okay, so I'm now setting up my second phase. This is the capsules themselves, the ones we saw in purple at the beginning. And I've set them as capsule particles. So that's a predefined type within STAR. And all we have to do is just set a length and a radius, and it will make our particles for us, and we don't have to worry about designing them ourselves. And again, they're solid. I'm not going to bother with any of the optional models, and I've skipped doing this, but the only thing I had to set was the density, and again, I set the Young's modulus. The wall properties were already set from setting up the previous phase. Okay, so now we've got our phases. We need to tell STAR how they're going to interact with each other. And before I do that, I need to set up one remaining type of boundary, because that boundary is going to have its own interaction. So in our particle domain, it defaulted to setting our boundaries to walls. We in fact want them as outlets. So whenever a particle hits the domain boundary, it will just disappear. We don't care about it anymore. It's fallen off our conveyor. My conveyor design is clearly poor if it's fallen off the conveyor, so we're not going to bother about it. We don't have to sweep them up off the floor. But the other boundary we need, as I mentioned earlier, within this domain is I want to have these filters here, so that when the particles hit the filters, they just get removed. So that's why I did the subtraction operation to give me these surfaces. So I've got these filter surfaces. I'm going to set them as outlets. But because I dropped my Young's modulus on my particles to speed up the calculation, it's kind of throwing the physics a little bit, and it's allowing my capsules to fit through these holes even though they shouldn't be. Now, what I should do as an engineer is I should just up my Young's modulus and deal with slightly longer calculation time. But because I wanted to cheat, and also because I wanted to demonstrate this capability, I'm instead just going to say that the capsules are not allowed to fit through this boundary. So I set that boundary to phase impermeable for the capsules. And the reason I just did that now before setting up the interactions as I'm doing is because now I have that phase impermeable boundary type, and I will need to define what happens when the capsules hit that boundary. So now I'm going to go through the phase interactions for both the capsules and the spheres and all the types of interaction they can have. So with themselves, with the walls, with the spheres, and the same for the spheres. So starting with the capsules onto the capsules, and just rename this so we can keep track of which of our different interactions we've got. It pre-populates our model DM phase interaction and tells us that the phases were the ones we selected. Now for the capsule model, we only have the linear spring option as our contact model. When we get to the spheres, we'll see that there's many other options available. I'm going to turn off rolling resistance, which is used if you need to add some extra resistance to account for roughness or different shape to the one you're actually modeling. We're not doing that, so I'm going to turn that off and just have the basic interaction in the linear spring model. For the linear spring model, I need to set a few different parameters: the friction coefficient, the restitution coefficient, and the spring stiffnesses. I'm going to leave the friction coefficient as it is, but this restitution coefficient is a little bit high. 0.5 is kind of like a bouncy ball, so we're going to drop those to about 0.1. I had to iterate a little bit on the spring stiffnesses. Ideally, you would have some material properties or something, but I'd made these capsules up. I had nothing to go on, so I just iterated on those until I got a sensible interaction as the particles first fell out of that injector, which we will see later. So then I just copied that interaction. I'm just going to kind of skip through quickly, but copy that interaction, adjusted the phase interaction so that it's capsules versus the wall now, change the properties, again, the spring stiffness, and then I just skipped there, but I've done the same thing for all the other types. So when the capsules hit the spheres and when they hit the impermeable boundary. So now I'll go through and do the same thing with the spheres. So here are the spheres interacting with the spheres. And the reason I've shown this separately, I didn't just skip this, is because we have a few extra options when we're just modeling spheres. We can see that we've got the Hertz-Mindlin model, and we've got a couple more that weren't available before. The Hertz-Mindlin is pretty simple to set up because it just requires friction coefficient and the restitution coefficients. You don't have to set the spring stiffness. That's all built into the model. So then I created another interaction for the spheres with the wall, and the only one that remains is spheres versus the impermeable region, but I haven't set up anywhere that that's possible within the calculation, so I don't need to set that up. If I'd not set up any of these interactions and you tried to run the calculation, it wouldn't work because sorry, just a sec, because it would know that interaction was possible and wouldn't run. But because this interaction is not possible, we don't need to bother setting it up. Okay, so the last thing we need to do in terms of the DEM setup really is to create an injector. So you just saw me creating a little cone there that sits inside our feed funnel, and then I've just created an injector, and I'm going to set that injector to be that cone. And we're going to need two injectors, one for the each for the two types of particles. So I've set this one to the capsules, and I'm going to set the type to a lattice injector, which is just going to create an XYZ grid within that cone. And I set the input to the injector. There's a few different conditions we can change. I'm just going to basically leave it at the defaults, but set particle flow rate rather than mass flow rate, so I know how many particles I'm getting per second. And everything else is pretty much configured as default. I'm going to set 0 velocity. I'm going to change my cylinder height and radius. That just sets the size of the particles. So for one defined phase within the physics that we did, we could create multiple injectors and have multiple sizes coming out. Or we could change the size from a constant. We could set it on a distribution, and I'm going to do that in a minute for the spheres. Similarly, we could have particle flow rates changing with time. I'm keeping it simple, just setting it a fixed flow rate. For the orientation, we could have them all oriented the same way. I'm going to kind of set them on a random normal distribution, so they all come in at a slightly different angle, and then just setting a spacing for my lattice, so they're all injected slightly apart and they don't immediately bang into each other. And we're going to copy that and create a second injector for the spheres. Most of the properties are going to remain the same. We'll change the phase, and we'll keep it using that same injector, so they're all going to come in at the same point. And there's not really much we need to change. We'll keep all the velocities at 0. We just change that particle diameter to use a normal distribution to represent different sizes of debris that have been created during the manufacturing or previous or the coating, like the example that Adam was showing earlier. And we'll add a few more particles into this one so that we've got a good ratio when it comes out. Okay. So we've sorted our geometry, we've defined the physics, we've set up our regions, we've set up the injectors. There's just a couple more tweaks we need to do in the solver settings. The time step here, I'm going to leave at default of 1 × 10⁻⁻3. This is for the DEM, when you don't have any CFD, no fluid physics involved. This is basically just a frame rate that's going to come out when I save my images for my video later, because the DEM time step has its own substeps, and the DEM time step is controlled by the settings within the DEM solver, not explicitly. You choose several factors, and they all affect the DEM time step. So this doesn't really affect how long the calculation takes to run. It will just affect how often you'll get a pretty picture out at the end. The only other things I'm going to do are turn on load balancing, which is going to rebalance every 50 iterations. It's going to rebalance the particles to different processes to make sure that we're running in parallel efficiently. Similar idea for the reordering frequency within the DEM solver. And then I'm going to change 2 things which are going to speed up the DEM calculation. Firstly, the time scale. This is related to the Rayleigh wave time scale. Default's 0.2, the resolution of that collision that it's going to resolve 20%. I'm going to change it to 0.3, which will just speed it up a little bit, but it doesn't really mess with the physics too much as long as it remains stable. I'm also going to turn on verbosity, so that every step it's going to tell me how long it's spent on each stage of the DEM calculation. And that's really useful when setting up a calculation, so you know, has it spent all the time on contact detection, which particles are contacting each other, or is it spending the time on the physics itself? So as you add more complex physics, for instance, the erosion, or if you were running non-meshless DEM and you had heat transfer and other stuff involved, then that verbosity would tell you where you're spending your time in your calculation. And the final thing I'm going to change is this skin value down here. This basically sets how far a particle is able to move in each time step without it checking whether it has contacted anything. And there's a formula for what you should set this to, available in the documentation. And it just reduces the time spent on contact detection, because if a particle is barely moving, then you know that it's not contacting. And then secondly, on here, we're going to set the stopping criteria. Different to running a simulation which involves a fluid, with the meshless DEM, we don't need any inner iterations. The sub-stepping is all controlled by the DEM solver. So we only have one iteration, one inner iteration. We'll set 60 seconds as our physical time, and then we can turn off the maximum steps because that's not relevant for this calculation. Okay, so at this point, the simulation is set up. We maybe spent half an hour doing this, and we're ready to go. We could just hit go. It's not going to be a very exciting simulation because all the injected particles are just going to fall down and sit on this conveyor because we haven't set up the motion yet. So we're going to define the motion in 3 stages. Firstly, the tip and the bucket those parts are actually going to move. For the conveyor, we'll then set up that the walls have an inferred velocity, but the parts don't actually move. So that's a different type of motion. So we'll start with the tips and the buckets, and this is just under tools motion. In order to define and quickly update my design of the conveyor and how much everything was moving, I created a load of parameters already. And the one we're going to need here is the tip center of mass. So this is basically, where is this tip going to pivot about? And the rest of these we're going to use in the functions that define this motion later on. So creating a new rotation motion for the tip, we'll set the axis so that it moves around the y-axis, and we'll set that origin to the tip center of mass, which was that vector parameter that I mentioned just now. We're going to leave the rotation rate itself blank, because we're going to feed into that from a report based on the weight that's in the bucket. So we'll set that up later. The only other motion we need is the bucket motion. That's just a simple linear translation, and again, we'll set that later. But by setting up these motions now, we can go back to our regions and we can tell them that their motion is defined by those two motions we just set. So they're no longer stationary. The buckets are controlled by the bucket motion, and the tip is controlled by the tip rotation. And by setting those, we unlock a couple of field functions, which we're going to use in the next stage to define our motion. So I'm going to create a report which is just going to tell me what is the current rotation rate of this tip. And I'm going to use that to basically, with an expression, say, if the tip's rotating, I don't want my conveyor moving, because if the conveyor is still moving and the tip's tipping in, then you're just going to throw all your particles on the floor. And I'm just going to go through and set the tangential velocity on each of the surfaces of the conveyor using just a number, a speed multiplied by that control that we just created in the report. For the slope and the downward slope, I've created a couple of coordinate systems, local coordinate systems, which just define the x direction along the axis of the conveyor. I'm going to use those to define the motion as well, to make sure that I have control over the velocity in the correct direction, as seen here. For the slope as well, I made sure that it didn't stop completely, because otherwise all the particles just ran to the bottom. My design was even worse than it already is. So then I just skip through and do the same thing for the other two parts of the conveyor, so the moving part. With the filters, in real life, you wouldn't be able to make a filter move, but my design was that bad that I gave them a velocity anyway, just because otherwise all the particles are bunched up here. It wasn't a very good conveyor, because they all got stuck. Okay, so the final set of the final stage of defining the motion turned out to be a little bit more involved than I had anticipated, just because of the way I designed it wasn't very good. But effectively, I just set up a monitor that says what's the current rotation rate, and then I create another report which integrates that over time and tells me what's my angle for my tip. And I'm going to use that along with measurement of the particle weight within the bucket, within the tip, and then later within the bucket. And this is the only kind of real relevant thing to DEM here. The rest is just specifics to my rubbish conveyor design. That we've got the DEM boundary force accumulation model, which we defined earlier when we set up the physics. And I'm going to have it report me the average total in the time step. So basically the total mass or total force on both the tip and the bucket, the time step. And I can create a report on the sum of this value, and basically it's going to tell me what's the weight within the tip at any one time. And then I can set up a mean, a monitor on that particle weight, and then take a moving mean, because otherwise you end up with spikes in the weight as the particles hit. But once you average that over a little bit of time, then you get a weight. So now I create an expression and I basically say, okay, if the weight gets above a certain amount, let's tip our bucket, tip the tip. And then this is the definition of that expression, but it ended up basically saying, turn to a certain angle and then turn back. And that controls the tip motion. I'm not going to go through the same thing again for the bucket. Basically the same idea. It measures the weight using the DEM boundary force model, and then it checks the current displacement and makes sure that it's sitting underneath the bucket at any point in time. So I've got those two final reports, the expressions I created to set what's the current bucket motion, which I assign to that motion, and what's the current tip rotation rate, which I assign to the tip rotation motion. So with those both set, that's the final stage in the setup. Kind of all that motion stuff at the end, you wouldn't need it in many DM applications, but that's how, and there's probably a better way of doing it for sure, but that's the way I set up the motion so that this setup would measure the weight and then move appropriately. I set up a few more monitors and some plots to make sure that my motion was behaving as intended. So this sees the particle weight in blue, the mean, as the particles fall into the bucket. Once it reaches a certain level, then it tells the tip to start moving, and you can see the tip angle over here in blue changing. Once it reaches a certain angle, then it starts dropping particles into the bucket, and eventually all the particles have fallen out of the tip, no more appear in the bucket, and the variance of our bucket weight drops, and that tells the bucket it's allowed to move. So then the bucket moves and brings the next one in place, and then the whole cycle repeats. Now I don't expect you to really understand this. I've explained it far too quickly, but or rather follow along. But we'll see it in the video in a minute. And it's a lot easier to see these things. I mean, I didn't really understand what was going on here until I created an IC scene and then used a video to see what was going on. This is just a kind of a regular scene setup in STAR. The only difference that, to a normal setup is that I've used the particle model to scale these points so that they are in the exact orientation and size of what we're actually modeling, so you can see them interacting with each other properly. I've also turned on advanced rendering to get nice pretty shadows and stuff, which considerably slowed down the calculation because it was spending almost as long generating the images as it was on the actual calculations. But it's nice for a demo like this. In reality, when you're running a calculation just to look at the results, you wouldn't turn that on. So this is the resulting simulation. We've got our injector, which we set up in here, injecting two types of particles, the spheres and the capsules, the spheres being of a different normally distributed radius. They're all interacting with each other and the walls according to those interactions we set up. Passing along this conveyor using the tangential vector velocities that we have assigned to the surfaces of both the flat here and the slope. They then pass over this filter where we set a boundary such that if anything passes through the boundary, it's removed from the calculation. We set that phase impermeable to our capsules so that the capsules wouldn't fall through. And then the particles fall into this tip. We're using the DEM boundary force model to measure the weight within that tip. And once it reaches a certain amount, we're going to stop the conveyor and we're tipping the tip. The tip puts all the particles into the bucket. The bucket is again measuring the weight that's landing within it. Once it reaches a certain amount and once it's stopped changing because the tip's empty, then the bucket moves along. And that's pretty much it. After seeing this, I then slowed down my conveyor and it considerably improved my filtering because it was spending enough time over the grid and actually filtering out most, if not all, of that debris. But obviously in my pill factory, it's slowed down my processing rate. So I've had to sacrifice how fast I can put my pills into my buckets in order to make sure that I've not got all this debris. I also tried a different design. This is really simple to do. You just go back into the 3D CAD and you change your surfaces, and then you right click and update your parts, and you clear your solution and you go again. You don't need to remesh. You don't need to do any more physics setup. You just need to make sure that your boundaries are still in the right place as you defined them before, in case the way I split it up, for example, I had to resplit it up. But other than that, it took maybe 10 minutes and I was off again with a completely different design. This one was also terrible though, so don't judge me on my conveyor filtering capabilities, but maybe judge me on my mesh-free DEM workflow. So with that, I'll hope that I haven't been talking to no one for the last however long, and open up to questions.
Excellent, thank you, Max. That was awesome. Jonathan, can you open up the audio for questions?
Sure. So everyone, first off, thanks, Max. That was great. Everyone, thanks for sticking around. If you have questions, I would invite you to put those in the chat or in the Q&A panel. If you'd like to ask a question out loud, just send us a message as well, and I can give you permission to talk. But a couple questions, I guess, to start with. Maybe Max, you didn't really talk about the particles falling through the grates. What happens to those? Can you like measure the mass of those small particles, or what could we do with that?
Yeah. So at the moment, they're just deleted from the simulation. Basically, it's treating it as an outlet. But there is one of the models I didn't turn on with DEM is the boundary sampling model, and that will just basically track the particle IDs and the details of the particle and when they pass through a boundary. So you could set that up for one or all of the filters. You could set it up for the floor underneath to see how many are ending up on the floor, and it means that you can track where and when they're falling out, but you don't have to keep computing where they've gone after that. So you kind of deleted them from the calculation, which will keep your speed up, but it means that you can still find out, okay, well, how effective was I? Because everything I've shown here is very, very qualitative. It's like, oh, well, we can see that there's more particles here now than there were in this simulation. But yeah, it would be perfectly possible, and you could do the same thing and track, as well as measuring the weight on the bucket. You could use the boundary sampling to say, okay, well, at what time do particles impact on the boundary? And you could make it very much more quantitative to allow proper analysis rather than just kind of eyeballing it from these videos.
Okay, yeah, awesome. And that kind of lends itself to the next question that we had, which is a little more of, like, is a process like this able to be optimized? And I think kind of a sub question for that is, like, can we parameterize the grate size? Can we parameterize the conveyor speed so that you could turn to something like HEADS and have it evaluate a bunch of combinations and evaluate, what's the most efficient in terms of not getting extra particles, not being too slow, things like that?
Yeah, I don't see why not. I mean, you would just in your 3D CAD, you could expose the parameters which created these holes so that they could be controlled from HEADS, and then you would set up the boundary sampling, set up a report on that, and then use that as the output that HEADS would use as a, I can't remember the right terminology, but it would use it as a metric for how good the design was. And you could change the particle flow rate. You could set up the particle size. All of those could be controllable inputs from within HEADS.
Cool, thank you. Additional questions, I guess. Again, still welcome any questions in the chat or the Q&A, or let me know if you want to be unmuted. Max, do you know, is there like a specific version of STAR that people would need to be able to have this capability?
Yes, so this mesh-free DEM is only available in the latest version, 2021.3. Everything before that, you had to make a grid. Each of these surfaces would have had to have been part of a solid sealed body. So your workflow, as well as Adam said earlier, it's maybe 5 times faster to run, but I would probably say it's almost 5 times faster to set up as well for a case like this, because I would have had to have worked a lot harder on the 3D CAD to get it right in order to be able to mesh it.
Okay, yeah. And along those same lines, you said faster to run. Can you just kind of give high-level details about the type of computing resources you used for this demo, how long it took, things like that?
Yeah, so I ran this on my local machine, which has 8 cores. I can't remember the specs of the cores. But with this being only around, I think the peak was about 4,000 particles or so. Really, I would have only needed to run it on 4, because once you get above about 1,000 particles per core, you don't really see any benefit. So I could have run it on 4 cores. And this, so this one here, I think is 19 seconds, and it ran in about 10 hours maybe on my local machine, but that's with this advanced rendering on, and that was taking quite a lot of time. I think it was probably 30 or 40% of the time, if not more, was spent because I could see it every time it paused to save the image. When I was first setting up the motion and kind of working out how the motion worked, I would say it would run about 30 seconds in maybe 6 or 8 hours. Now, it's fair to say I did cheat a little bit with the Young's modulus. As I said, they're a bit soft, these particles, so increasing the Young's modulus would increase that runtime a little bit, but yeah, that's the sort of ballpark I was looking at for this case.
Great, thank you. Yeah, and thank you, for an awesome presentation. This was really great. Thank you, Adam, as well. I don't see any other questions in the chat or Q&A tab, so.
Hey, Jonathan, I have one question.
Oh, yeah, sure.
If anybody wants to get this SIM file to run it on their own installation of STAR-CCM Plus, then reach out to us. I've put my name here and phone number and email, so that if you basically want to get that SIM file, give us a call or an email and we can send it to you. That's it. Thank you.
Cool. Thank you, everyone, for coming. Have a great afternoon.
Thanks, everyone.